Okay, so last time I started this new topic that there are infinitely many primes in arithmetic progression. By the way, so earlier I had mentioned other courses in ISC which have some overlap. So this representation theory courses, for example. But this particular one, I see Soumya Das is giving a course. I think he covers this also there. I mean, much more, much more. But anyway, so that is some of you may be taking that course. So he's an actual number theorist. I am far from it. But this is a nice one. So I wanted to tell about it. So what is the theorem we are headed towards? The big theorem is that there are if you take any arithmetic progression, a plus b, a plus 2d, a plus 3d, and so on, then if a and d are co-prime, then there are infinitely many prime numbers inside this arithmetic progression. So there is a bit of echo. Second again. Yeah, now there isn't. Okay, so okay, no problem. So if a and d are co-prime, then there are infinitely many prime numbers. In fact, what we will show is that the sum of reciprocals of primes in this arithmetic progression is in fact infinity. And a stronger statement, which we may or may not do, is that the sum is actually, I mean, so when you fix the, oh, actually I wrote something wrong here. So we are talking about modulo. What is this? Yeah. So this is okay. So here I have written P congruent to K mod M. If we consider that, arithmetic progression, so that is K M plus K 2M plus K 3M plus K and so on. So M is D now. Okay. So and A is K. So then the number of different arithmetic progressions. So modulo M, some arithmetic if you fix residue classes modulo m, some of them will not contain any primes because they are all composite numbers. So the remaining ones, there are 5 of m many. So these are the number of those that are co-prime to m in 1 to m. So these are the ones for which it works, and each of them has roughly the same number of prime numbers. There are many senses in which one may want to prove that. Okay, there are different senses in which one can prove density. This is one way of saying it, that this sum of reciprocals up to x blows up like 1 over 5 of m times the way sum of 1 over p blows up. Okay, so this one, instead of this, one can write here equally 1 over this. So where this divided by sum of 1 over p over all primes less than equal to x, that whole quantity blows up like 1 over 5 of m. Okay, so in other words, the number in this arithmetic progression is roughly the same. Well, of course, we are not taking the number, we are taking some weighted sum, but you can do it for numbers too. Meaning, if you ask number of primes less than equal to x in this arithmetic progression divided by number of primes less than equal to x, that ratio goes to 1 over 5 of m. That much is true. Okay. And so last time we recalled that, okay, there are this infinitely many primes, there are many proofs. So I mentioned that there are elementary proofs in special cases. So just let me just remark. So simple proofs in very special cases. Okay, so somewhat like Euclid's proof. For example, so if you look at arithmetic progression, which is 3 mod 4, so minus 1 mod 4, which means 3, 7, 11, and so on. So in this arithmetic progression, so there is so in Apostol's book, he gives a very simple proof for this. So just to illustrate, it's like possible. In some special cases, apparently it is possible, but in general not. So here, if there were all the primes in this arithmetic progression here, then you do it like before. Okay, so P1 is 2, let's say. P1 is not 2. P1 is 2 is not there in that. So P1 is maybe 3. So you take the product of all those. And multiply by 4 and subtract 1. Okay. Yeah, so this is what you do. It's a bit like Euclid's one, right? I mean, where you multiply the primes and add 1. Here you multiply them, multiply also by 4 and subtract 1. Okay, so this must have a prime factor other than P1 up to Pk. So this must have a prime factor other than, because none of those divided. So implies all prime factors are 1 mod 4. All prime factors, so 2 cannot divide either, right? I mean, 2 is not possible other than P1, P2, Pk, and 2 is also excluded because it is minus 1 mod 4. So what remains? So you have removed all prime numbers which are minus 1 mod 4. So what remains are plus 1 mod 4. But then when you multiply numbers which are plus 1 mod 4, of numbers which are 1 mod 4 is 1 mod 4, right? Is also 1 mod 4. So this will not, this cannot be equal to this. So contradiction. So there must be infinitely many prime numbers here itself. Okay, so you excluded the other things. So this is a bit like Euclid's proof. So what I read, I don't know this particular proof. Apparently there is some special proof like this, not like this, not like Euclid, but special proof using some basic algebra for AP of the form 1 mod, what is the divisor I used to take? 1 mod D, let's say. So for 1 mod D, it is okay. For A mod D, there isn't. Also, another special proof I saw, I'm just reading that paper just for fun. It's not something that we will discuss here because the whole point is we are giving application of Fourier analysis. So Selberg has an elementary proof. An elementary proof of Dirichlet's theorem, the full, not some special case, though the conclusion is not as strong as this. So he could not, I mean, from what I see, maybe somebody has sharpened it later. It is from 50s or 60s like that. So I'm just looking at that paper. But so there, the conclusion is not like this. What he shows is that this ratio is not going to 0. So there is some constant, but that constant, I mean, lower bound of a constant, but not 1 over 5 of m. So he doesn't quite show that. So he has, but it shows that there are infinitely many primes, even that it has a positive density. Okay, so that is what it shows. So these are some things I have seen. But other than that, but our aim will be to do the Fourier analysis proof. Okay, so any questions, comments? Before we start, I mean, it will take a while. It will take 2-3 lectures. So.
Manju, can you explain again what this phi m was?
So phi m is just the how many numbers are co-prime to m in 1 to m. So phi m.
Okay.
Okay, in 1 up to m. Is that k is co-prime to m. So this is actually, I mean, so these are the numbers which form a multiplicative group. I mean, so if you take z mod m, So we will denote Z mod M star is this set. Okay. So Zm is, you remember, 0 to, I mean, okay, if you want I can, so yeah, so I could have included 0 is included here, but anyway, Zm star is this is a group under multiplication actually. So this is a group under multiplication. So which are modulo, I mean, so coprime to M, they form a group under multiplication, and so this is the size of that group actually. That's all. So when I go to an M is 4, it is 1, 3. This is 1 and 3 are the that they form the group, which is isomorphic to Z2. Any other questions? Okay. So then, right. So we'll. Yeah, so we will actually it will be so the presentations will be using will be of that group actually. So that Zm star. Anyway, so what is the point? So what is the overall idea? So the thing is, yeah. So we want to consider. We will want to. So we want to consider. So let's say a broad sketch. So so fix. So let me fix notation for now. Okay. I mean, so what is my arithmetic progression, which is A mod D. Okay. So this is A plus B, A plus 2D, and so on. So let me fix this notation. Otherwise, I'll keep switching many times. So let us consider this. So let us look at, so consider the sum of reciprocals of prime powers P in this. So for me, arithmetic progression will mean this. Okay. So P in this arithmetic progression. Okay. So this will converge. Of course, this converges for S bigger than 1. So if we can show, if this converges to infinity as if this blows up as S goes down to 1, that shows there are infinitely many primes, right? In the arithmetic progression. Okay, in our arithmetic progression, there will be, of course, if there are only finitely many, there is no way it can blow up. It will just converge to the sum of the reciprocals. So the question is, can we do something like Euler did? Okay, so can we do something like Euler did? So can we find a, so last time I gave a sketch of how sum of reciprocals of primes without any arithmetic progression, the whole sum of all prime reciprocals of primes is infinity. And the key idea was like this: summation 1 over n to the s we wrote as in this product form. I ignored all convergence issues. We'll do this in more generality. Okay, so I'll justify it then. But then from that, when we take log zeta s was basically log of 1 minus 1 over p to the s, and log 1 minus x is basically like x for small x. So this thing is like 1 over p to the s plus some things which are not going to bother us. So log zeta of s is this log of this is like summation p 1 by p to the power s plus some terms which stay bounded, whatever you do. Okay, so as s goes down to 1, this blows up because the left side blows up, because we know that summation 1 by n to the s blows up. So the log of that blows up, and therefore summation 1 by p to the s should blow up. Okay, so that is how we get that summation 1 by p is infinity. So can we do something like that here? That is the question. Okay. So what could be a sort of a naive sort of idea? Here we start with summation 1 by n to the power s, right? So naively, you take all n in the arithmetic progression. AP will always mean this arithmetic progression 1 by n to the s, and then try to can we write this as a product, for example? So it's not even if you do that, I mean, okay, so as it is, it's not clear the value of this, because just because n is in the arithmetic progression doesn't mean its prime factors are in the arithmetic progression. But whatever it is, so this is so I'm just saying this ultra naive thing to motivate what we will actually do. Whether summation 1 by n to the s, n in the arithmetic progression, can such a thing have a product form? There is actually no reason to expect such a thing. This won't work. So what works? That is the key point. So this is where characters come in. Okay, so let's go back to this product formula. So the key idea was, this was the fundamental theorem of arithmetic, that every number can be written as a product of primes. Okay, so so if we look at this, so let's just look at this. So so again, I'll come to the convergence issues in a moment, but so if you look at something like summation an by n to the s, n equals 1 through infinity, what you are trying to do is an is 1 if n is in the arithmetic progression and 0 otherwise. That's what we are hoping for. But can we write this in a product form? In primes. So of what? Let's say we will try to write like this: AP over P plus AP square over P square plus AP cube over P cube, etc. Is this true? Can we write this? So if you see, forget convergence, but when you take product from fundamental theorem of algebra, arithmetic, more or less it's like that. But except when we expand this side, the expansion, what will you get? You will get sum over all P1, P2, Pk over all k greater than equal to 1, or even 0. Okay, if I write that separately, 1 plus, so sum over k greater than equal to 1, we take a certain number of primes, right? So then you will get, and some powers for them, e1, e2, ek. In the remaining primes, we will take the factor 1. In these primes, we take P1 to the E1, P2 to the E2, Pk to the Ek. So we'll get something like P1 to the E1 up to Pk to the Ek. But what we'll get in the numerator is A P1 to the E1 product dot 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 A Pk to the Ek. Right? So, but on this side, we have an by n to the s. So every n occurs exactly once. Okay, so each n occurs exactly once. So this works if an is a p1 to the e1 dot 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 a pk to the ek. If n is, this is the prime factorization of n. If n has this prime factorization, then an should have this factorization. So what does this mean actually? So this is same as, so what does this mean? When n is a product of this number, an is a product of those numbers. This is actually exactly the same as saying a n times m is an times am. If I have this product formula, a n times m is a n times a m, then certainly this type of thing is true. So this can't be any numbers, but they have to have this type of property. Okay, you don't even need this. What do you need? Actually, you need this for mn coprime. When m and n are coprime, a and m should have this product form, because anyway different prime powers are going to be coprime. So it happens often in number theory that lot of functions have this property for coprime numbers, but not for all mn. Although in the moment we'll see that for our situation it will have this property for all m and n. But this is same as question?
Manju, can you hear me?
Yes, yes.
I think you are missing the S on the right hand side.
Okay. Yeah, thanks. So this whole thing to the power of yeah. So I should have put here S everywhere. P to the S, P to the 2S, P to the 3S, and this is this number to the thanks. So just like here, is that where did that 1 by n to the s is product of 1 plus 1 by p to the s, p to the 2s, etc. So here this should have the power s, and then the reasoning is so an should be but the coefficient should match, so an should have this property, which is same as a times a of nm is an times am for m and n coprime. So it's like a homomorphism like property, right? You see somewhat, I mean, but only for coprime things. Okay, so this is this. So if this is true, then it works. So is that true for the thing that you are taking 1 on? So if you take a function which is 1 on, so just for specificity, if you can write down, say 1 mod 4. So you have the numbers. You will have, just to keep something concrete at hand. So you have something like the arithmetic progression is 1, 5, 9, blah blah blah, and or you can take a equal to 3 and d equal to 4. That will give you 3, 7, 11, dot dot dot. So let's say you take one of these APs. So keep this as a running example if you like to keep in mind. So is this true? I mean, if I have the indicator of this arithmetic progression, so I have a function which is 1 on such things and 0 otherwise. Is it true? Is it true that it has this multiplicative property? No, it is not. I mean, so you can see that, right? I mean, what is a counterexample? So such a thing is not true. You can have 3 into 3 belongs here, right? So 3, if you put the indicator of this first arithmetic progression, then A3 will be 0, right? But oh, okay. So that's not good. I should take 3 into 7. A3 should be 0. A7 should be 0. But 3 into 7, 21 belongs here. So A21 should be 1. So that violates this property. So it is not true for that naive thing. But what? Okay. So that is a problem. So we can't do that. So, but before going further, before telling what works, let me observe another thing, that if in fact, if we further have AMN is AMAN for all MN. Okay, so this thing is called, this property is called multiplicative. This is the more common one that occurs in number theory. So you say A is a multiplicative function. A from natural numbers to, in general, it can be to complex numbers, is a multiplicative function. So this one is a little unusual. I mean, it's a bit less, it's less commonly seen. But if such a thing, then we say that A is a completely multiplicative function. So this is completely, so here there is no coprime condition. It's always true. Okay. So if we further have that, then we can go a bit more. Then prime powers will be AP raised to the power E, right? Because even prime powers, so P square, P is not coprime with P, but we are asking for completely multiplicative, then this is true. So what happens then is, so again, the question of convergence and such things I will have to come back to, but we will get n equals 1 through infinity an by n to the power s will be, so this we already have, but this is AP, this is AP square, AP cube. So you see you have a geometric series here. So you get a product over P and sum over j equals 0 through infinity AP to the power j over P to the j times s, which is actually product over primes. This is a geometric series. We get 1 over 1 minus the first term, which is AP by P to the power s. So this is even more closer to the Euler product formula, which we had here. So we went from here to here because it's a geometric progression. So that is true if A is completely multiplicative. We get this. So which is even nicer. No, I mean, it is a general point that you can define some analytic function to get explicit product formulas. It's very unusual that you get them. So it is actually, these are rather special functions, very special. And especially this form is even nicer. Okay, so this is true, which is even nicer. So this is fine. So this works when you take A to be multiplicative. And the remark that I made is that naively taking things like does not work. It's not multiplicative. Okay, so what is multiplicative? So what is so example of multiplicative? In fact, these will be completely multiplicative functions. So these will be the ones of interest, but just to tell you, since I said these things, so there are many functions which are actually multiplicative but not completely multiplicative. So a very famous one which occurs, which you may have seen in elementary number theory classes, is the Mobius function. So it is defined as mu of n is 0 if n has a square factor and it is +1 if it doesn't have a square factor, then it's a product of distinct primes. So the number of those may be even or odd. So these are distinct primes. So if n has a square factor, then some prime square will divide it. Then you set it to be 0. +1 if it's a product of even number of distinct primes. -1 if it's a product of odd number of distinct primes. This is a very famous function which occurs in number theory. I mean, it occurs in a lot of, in very close context actually here. But the point is that this is a multiplicative function which is not completely multiplicative, right? So for example, you take two of these with odd number of things, then the product will be, okay, actually, so sorry. So you take two of these numbers, I mean, you take n square, for example, that will become a number with a square. So you don't get the product of one with itself, but you get 0. So this is an example. This is a multiplicative but not completely multiplicative function. Okay, so that is not an example. So the examples of interest for us will be in fact completely multiplicative. What are they? So you look at Z mod. So what is the symbol I fixed? The D, right? D is the divisor. Z mod D. I used to write ZD, right? So I just write ZD. But you take ZD star. Okay, so you remember this is K in 0, 1 up to D minus 1 that are co-prime to D. And you take a this is a finite abelian group actually. So a finite abelian group. So it has characters. So the cardinality is phi of m, and phi of d, and that is the number of characters. Okay, so I will write down examples just to so that people who prefer want to keep in mind some explicit examples. But now, for now, just abstractly, let's consider let chi be any character. Of ZD star. So chi is a homomorphism from ZD star to the unit circle, right? Unit circle in the complex plane. You take any character, but now I want to define it on all integers. So this is defined on the group. So this is a function defined on this. If you want these numbers 1, 0 to D minus 1, but only those that are co-prime to D. So extend it. So extend it chi to all natural numbers by the obvious way, more or less the obvious way. So chi of any k is going to be, so you just do it with modulo this. Okay, is chi of k, is chi of, if you want k bar is the residue of k mod d. But that is only if k is co-prime to 1 to d. Otherwise, if k is not co-prime to d, then you set character to be 0. Okay, so we will define chi is now defined on integers. Okay, non-negative integers. So just to have example, that same example, so let's take these particular, you take these for, so let's say d is 4. When d is 4, Z4 star consists of 1 and 3. Okay, 1 into 1 is the identity, 3 into 3 will give you 1 mod 4, right? So this is actually isomorphic to Z2 by sending 1 to 0 and 3 to 1. Right, so you know what the characters are. There will be two characters. One is a trivial character. So chi 0 is the trivial character, which is and chi 1. Okay. So chi 0 of so chi what chi 0 of 1 is, chi 0 of 3 is 1. In chi 1 is the non-trivial character. It sends identity to 1, but the other element to minus 1, right? So these are the only two characters. So in Z2. So you can send the non-identity to minus 1. So these are the ones. So when you extend, it's the same. I mean, I will just use the same. So chi 0 of k will be, it's not 1 for all k. So that is a small point one should keep in mind. chi0 of k is 1 if it's 0 if k is even, because that's when it's not co-prime to 4, and 1 if k odd. Okay, so chi1 will have 1 if 1 mod 4. I mean, if k is 1 mod 4, and okay, so maybe I don't need to write maybe. So, but so if 1 if k is 1 mod 4, minus 1 if k is minus 1 mod 4, and 0 otherwise. Otherwise is if it's an even number. Okay, so there are two such characters. So this is just to have example in mind. Actually, the case of 4 is quite simple, and it's good to see proofs in that case. It makes it simple. There's a reason, because as we saw in, I mean, we were doing Z2 recently, right? So the characters are actually real. They are not complex valued. So some things simplify, some things don't, but okay. So now chi is actually completely multiplicative. So the point is, observe, chi is completely multiplicative. Because it's clear, if you multiply two numbers, if even one of them is not co-prime to D, then the product is not co-prime to D. So it will be 0. So we'll have 1 0 factor, and that's okay. But if they are both co-prime, then the product residues go well, right? So product of residue of product of two numbers is the product of the residues, provided they are co-prime. So then it is okay. So it's completely multiplicative actually. So hence we get this. If you modulo all the convergence issues, is this okay that it is completely multiplicative? So modulo that, we get this amazing conclusion. So then we get that if you look at this one, chi of n by n to the power s, n equals 1 through infinity, that is equal to product over primes of 1 over 1 minus chi of p over p to the power s. So we do have this product formula for characters in this nice way, because it's completely multiplicative. We don't even have to write these sums. We have this formula. Is this okay? So this left side, it is denoted. So this is defined. We will define this as L chi of S. Okay, so this is Dirichlet L function. So there are lots of things called L functions in number theory. I don't even know if there is a, what exactly is an L function. I don't know, because lots, for anything, it's some kind of a, they use it in a very generic sense also, as a general generating function of some sort. But this is what is called Dirichlet L function. So, okay, so this is the standard word is used is L, and this is called Dirichlet L function. So anyway, so this is again convergence issues I have to come to, but this will be have this product form. Okay, any questions here so far? So except convergence, everything else is okay. I think one has to worry about for what S is this, and what is the sense of convergence. Is it converging? Product is converging, sum is converging. That is something we have to ask. But other than that, everything here is quite rigorous. There is nothing missing. Is there any question? Comment? Okay. If not, so but that begs the question. See, what we wanted was to to address this Dirichlet question. So is there a question?
Yeah. So, sir, we said we have two characters, right? So this
for 4, yeah.
Yeah. So chi is completely multiplicative. That holds for all the characters.
Yes, it holds for all characters with all D. You take any D and any character, it holds. So all of them now I'm thinking as functions on integers. Okay. You take any D you fix any d and you take start with a homomorphism of that into zd star into this, but I extend it as a function on natural numbers. And all those are completely multiplicative. Yes.
But is that easy to check? Or
Oh,
is
yeah,
it?
yeah. So I just said in words because it is easy. Because you see, what I mean, so it is, this is the definition, right? So you take two product of two numbers, k and l. If if one of them has a common factor with d, then kl will also have a common factor with d. So chi of k will be 0, chi of kl will be 0. So that part is okay, right? So the only case you have to consider is when k and l are both co-prime to d. Then, but then k bar, so then that's the point that the residue of kl is same as, I mean, what I am writing is kl mod d is same as k mod d times l mod d if k and l are co-prime. This is true in general. If two numbers are co-prime, then the it's easy to see. If you don't see it, I mean, just try it for a moment. So then you will see it. So here, for example, you multiply two numbers. If both are of 1 mod 4 type, then you are multiplying 4j plus 1 into 4l plus 1. You see, you will get some multiple of 4 plus 1, etc. So there are a couple of cases. But in general, it is not hard to see that.
No, that should be K and L in ZD star.
Well, here I just locally use this notation that k and l are integers. K bar indicates the residue in. Yeah, so this one, okay. So yes, so this product is in ZD star, is what you are saying. Is that what you mean?
Yeah, yeah.
Yeah. So these are elements of ZD star, yes. But point is the residue of k and times l is same as product of the residues if they are co-prime. This is actually not hard to see. If there is any difficulty, you can ask. Just somebody can write in the teams also. If such questions are there. Okay, so that's why I have not written any further justification because it is easy. But this gives this nice conclusion that these Dirichlet L functions have this product formula. Fantastic, actually. So it's an unusual thing to be able to get such a formula, and they give. Okay. Any other questions? Okay. If not, then. But that begs the question of what is the point? Okay, so we thought that maybe it's naively that something like this would be helpful. Summation 1 by n to the s, n in the arithmetic progression. That is not, apparently that doesn't seem very, I mean, so, but now we have saying that, so that I generalized to putting some coefficient, figured out that you should take something completely multiplicative and then put characters. But how will that help here? So the point here is, so you can use characters to write other functions, right? Characters form a basis. So for example, so in ZD star, if A is in ZD star, as we assume, see A and D are co-prime, right? So A comma D I'm not going to use for anything. I already used A for something else, but okay. So A and D are going to be in the original definition of the arithmetic progression. If A, so we are assuming A and D are co-prime, then the point is, if you take the indicator function of A, can be written as a linear combination of characters. Right? You agree to this, right? So these are functions on as functions in, this is in L2 of ZD star. You can write any function as, okay, strictly speaking, I put a square root of the size of the group here. The way I defined Fourier coefficient, so that was sticking out. So we have this is the Fourier expansion. ZD star. So, and extend everything to natural numbers in the usual way. So you see that indicator that n belongs to, now let's not use A, n belongs to the arithmetic progression. That is, here n is congruent to A mod D. That's mod D. That's what I'm writing. That indicator can be written as a linear combination of characters. Right? So, as a linear combination, actually, in fact, what is this indicator A hat of chi, by the way? Is 1 over square root phi of D times indicator A inner product with chi, right, in L2 of ZD star. That's what it means. So, but that is nothing but 1 over square root of phi of D times, this is only non-zero at one point. So, this is actually chi of A conjugate. Because chi is in the second variable, you get the conjugate. So, this is actually chi of A bar. So, what you see is that, okay, before writing the general one, so maybe I write it here, sorry. So, this is actually 1 over phi of D, the two square roots combined, times chi of sum over all characters of ZD star of chi of A conjugate times chi. This is the function whose argument indicator A of evaluated at a point will be this. This is the Fourier expansion of indicator A. Is okay? So this we are just using general Fourier for any finite abelian group. We have this, and the indicator function has a very simple Fourier coefficients. I mean, it's just chi of A conjugates. Now this is in Z mod D star, but the extension completely holds. So if what I'm writing is, if you extend everything to integers like I did for characters, this side the extension will be, it is 1 on the residue class A mod D and 0 elsewhere. So in other words, indicator n is congruent to A mod D. Is written as sum over chi in ZD star hat. Sorry, here also I should put hat of what? Okay, so I have a 1 over phi of D here. And then I have chi of A conjugate and then chi of n. Sorry, is this right? Right. Okay. So is this okay? I mean, so if you extend to natural numbers, it's just this. You get for any n, that n is congruent to A mod D, you can write like this. So you are just extending this to any n, that's all. Which is okay. You're just taking modulo. Chi is itself periodic, right? Anyway. So it's going to work that way.
No, Manju, it should be chi of n bar and chi of dot.
No, this is chi of A bar. First of all, it is indicator n is congruent to A mod D.
Oh, then they're anyway same. But then why is it chi of n there? You're evaluating this at indicator n at.
This is indicator A at of n bar, right? That's what this is. That's what this is. Indicator that n has that residue. So you get chi of n. So I have written it in the subscript, but it is indicator A of n actually, of n bar, which is n. I mean.
Okay.
So I have chi of n on the other side, taking the same extension. And anything that is, yeah, okay. So that's all. Is this okay? Is there any question or is it all right?
Yeah, it is fine.
It's fine. Okay. So now we can, what were we interested in? For example, something like this. sum of 1 over n to the s over n in this arithmetic progression. If you like, you can write it with that. You can write it. So you can write this type of, so this is the way Fourier analysis is entering. We have a function which wants to pick out a particular residue class, right? And those functions are not nice, but you can write it in terms of characters which are much nicer. That's the whole point. Okay, so for example, as a corollary, you can write, so you just sum over all n in the arithmetic progression 1 by n to the power s. Here, this means n is congruent A mod D. So if I take that, so you will take this by 1 by n to the s and sum, and you interchange. This is a finite sum, so you can interchange. So you'll get 1 over phi of D sum over chi in ZD star hat of phi of A bar times sum over n in the arithmetic, sorry, you can just write, okay, n in the arithmetic progression, chi of n by n to the s. But for n not in the arithmetic progression anyway, this is 0, right? I mean, so this is actually 1 over phi of D phi of A bar times the Dirichlet L function evaluated at s. That's because for n not in the arithmetic progression, oh, sorry, what did I do? So why did I write n in the arithmetic progression? Hold on. Sorry, I did something wrong. So this is, sorry, with no, we are not doing. No. No, this is not correct. Sorry, I'm wrong here. So let me think what I wanted to write. So this is not correct. So chi of n is of course non-zero for other residue classes also. I mean, only things that are co-prime to, I mean, not co-prime to D, you get 0. For other things, you get non-zero. Okay. So it is, what is it I wanted to write? I wanted to write maybe n co-prime to D. Maybe. Let me just check. Hold on. Okay. Sorry. So I didn't want this actually. This is not useful, right? So what we want is actually, right. Sorry. Okay. I completely mistook. So yeah. So this is not, I mean, I gave some nonsense motivation that I got confused myself. What we want is this, right? What we want to show is sum of reciprocals of prime powers that diverges as s goes to 1. So let's take P. So consider, so let me erase this and write. So I don't want to take over all n actually. That was not correct what I wrote. I want to take over primes, suppose. Sum over primes in the arithmetic progression 1 by p to the power s. Okay. So what is this? This is, so indicator, so this is nothing but sum over all primes, that indicator p congruent to a mod d over p to the power s. Now we can write this in terms of characters like we did here. Indicator we will write like this. So we write sum over p 1 over phi of d sum over chi in zd star dual of chi of a bar chi of p over p to the power of s, right? So this we get. Now we interchange. So you get sum over, okay, let's pull the 1 over 5 of the outside. Then you get sum over all characters of chi of a comes out. Chi of a bar is here, and I write sum over p of chi of p over p to the power s. Okay, so this is the thing that actually is occurring here. You see, chi of p over p to the s is what occurs in this thing. Okay, so what about this? Okay, so there are actually, so this is actually, so let's use the symbols that we had now. Phi of d sum over chi of a conjugate times this is this is not the L function. This is only sum over p. Okay, so sorry, that's not correct. So let's leave it like that. So now this one, so I have 2 minutes. So let me just end with by saying, so what is the point here? So we are asking, so our goal is this left hand side goes to infinity as s goes down to 1. So we can work on the right side, because this is same as this, so we can work on the right side. But here it consists of two different types of terms. You separate the trivial character. Okay, so you get 1 over 5 of d times the trivial character, which puts everything to 1. What does that give? It gives us, since a is coprime to d, that will be 1. So that will give us sum over p, the trivial character by p to the power s. So this is chi 0 of p. So chi 0 of p is 1, right? For all primes, so that is actually 1. Sorry. No. Only those that don't divide d.
It's 1 o'clock.
Yeah, so this will be the, okay, so the trivial character plus 1 over d sum of all chi not equal to chi naught. So this is the trivial one. And these are the non-trivial ones. And chi of a bar times chi of p over p to the power s. The point is, so what the way the proof will proceed is that, so this one actually chi naught of p is not always 1. It is 1 if p doesn't divide d. Okay, if it divides d, then it is 0. But still, this one can show this is more or less like summation 1 by p to the s, hence blows up. S goes down to 1. The point to show is that you want to show the left side blows up. So this first term blows up. The main main point will be none of these blows up. None of these blow up as s goes to 1. So that is for chi not equal to the trivial character. It does not blow up as s goes down to 1. So now one term that blows up and a finite number of terms that don't blow up. So the total will blow up, right? So this will be the way we will do. And that is the key analytic thing to prove, that this does not blow up. For the trivial one, it is easy. This is more or less Euler's proof. But this is the one that we have to prove, that this does not blow up. Okay, so this I'll do in next and further class. Okay, so I'll stop here. Any questions, comments, etc. I'm happy to answer.
So can you say how this is connected